Sheesh, that's loud. Okay. So yesterday we looked at the relationship between how much of something you have in terms of how big it is, and how many of those things you have if you count them up to 6.02 times 10 to the 23rd, which of course you're never going to count that, but you can count by moles. And gratefully, we have the work of people from 150 years ago who have done this and figured out really, knowing how many moles of something is in a gas is straightforward. There's one number to memorize. You don't have to look at the periodic table. It is just that magical 22.4. And that's just an artifact of the fact that we define a mole and a liter independently, and then that just happens to be the ratio between them. So once we have that, then we can move forward with any gas. Doesn't matter if it is really light, if it is air, if it is anything, is going to have a mole at freezing that will take up the space of 22.4 liters. It just will, and regular pressure as well. So there are, again, several things that do have to be just right for this number to be true. It does have to be 1 atmosphere of pressure, so don't go diving in the ocean. It has to have freezing temperature. If you increase the temperature up to room temperature, in fact, the volume will be bigger. Not ridiculously larger, but it will be bigger. If you make it hotter than that, like a hot air balloon, then the volume will be even bigger. This is one reason why hot air balloons work, is because their number of molecules is less. Their number of molecules for every liter is less than the surrounding air, which makes it lighter. So all the surrounding air is more dense and pushes down, just like, do you guys know ivory soap? The soap that floats? Just like when you try to push that down, it pops back up. Or Cheerios. Cheerios always pop back up in your milk, okay, because the milk is heavier. The earth pulls more on the Cheerios than it pulls on the, pulls more on the milk than it pulls on the Cheerios. The earth pulls more on water than it pulls on the ivory soap. And so it has nowhere to go except up. Same thing with hot air. It's not that hot air and flame want to go up. It's that they are forced to go up by the heavier bullies pushing them out of the way. So next time you get in a hot air balloon, then be thankful for this rule, this mass-mole relationship. Sorry, the volume-mole relationship. Has anybody ever been up in a hot air balloon? One person. Never will? Don't trust him? Okay. All right. Have you ever been in a car? No? Only trucks. Okay. So but that number is one that is a starting point that can be adjusted. So yes, if you want to adjust it to be a little bit higher temperature, if you want to adjust it to be a slightly different pressure, you can do that. And the magic equation for this is what I like to call PIVNERT. So PV equals nRT. PV equals nRT. The pressure times the volume will get some number that by itself is meaningless, but it's the same number you get when you multiply the number of moles times the temperature times this other number called R that makes all the numbers work out. Okay? So you know what pressure is. Okay? But wait, let me take a step back. Do you guys know what pressure is? From like middle school and stuff? Like we were talking about the pressure in a tire, like 30 pounds per square inch or something, right? So it's the force over area. Pounds is a force, square inch is area. And so the more of that you have, the more you're pushing on the tire. And then, so that's one number, pressure. Volume, of course, is going to be measured in length, width, and height. And you could use meters cubed, but that's really big. A cubic meter is really big. So we use liters. And there are 1,000 liters for every cubic meter. So it's a bit more normal sized. Something you can handle as a liter. And again, N, we chose because originally we chose it because it was 1 gram of hydrogen, and then we chose it because it was 16 grams of oxygen. Now it's 12 grams of carbon. Whatever. The point is, it's manageable. It's a manageable quantity. It's not like it came down, from Mount Sinai with tablets. We just chose it because it was a human-sized thing. If we were ants, we'd probably have a different number. We wouldn't have 6.02 times 10 to the 23rd. It might be 1 times 10 to the 20th. I don't know, but so it's nothing magical. It's just a number we've chosen. You need to learn. And then T, we use temperatures in Kelvin. Kelvin. So to put up the dimensions here again, we're going to use atmospheres for pressure. We're going to use liters for volume. We're going to use moles for the amount of stuff. And we're going to use Kelvin. Now, Kelvin is just like Celsius, except it counts from absolute zero. Okay, now this R number is kind of like, good morning, Garrison, is kind of like this STP volume. It's just a number you have to memorize. So it's 0.0821. Some sources will say 0.6, but it has a lot of units. Okay, the point is that the units that you'll read about when you get to it, the units will just make all these other units work out. Liters, atmospheres, moles, and Kelvin. So don't be, too wigged out by the units that are there. But the key number is 0.0821. That makes this work out. It's a wonderful thing. Yes.
How does like 0 degrees work?
Right.
And negative. If you woke up one day and decided that was 0, how did that happen?
Okay. So there's a question here for those of you at home. How is it that we decided on an absolute 0? Is that what you're saying?
Like, because the weather, people can say it's 0 degrees.
Right.
But then it goes negative, so why is that not 0?
Right.
Why is 0?
Okay. So there are at least 3 very common temperature scales. And ultimately, it just comes down to convention. Remember, there are 4 ways to know things. One of them is we all just decided it was that way. So convention is we all just came together and said, this is what it's going to be. This is what we're going to do. So like, for instance, with distance, we use meters, or we use yards. We use kilometers, or we use miles. We just decided. Okay, maybe somebody ancient times decreed something, but now we're stuck with it. It just is. So with temperature, same thing happened. Way back when they were actually starting to get good thermometers in the late 1600s, early 1700s, they were actually getting good thermometers that would be accurate. They decided, hey, we better get some numbers here. So this guy, Fahrenheit, basically said, okay, 0 is going to be as cold as I can get. As cold as I can get, like in the weather in the winter. I'm just going to say that's the farthest down it went. I'm going to say that that's 0. And he was somewhere where it got cold. Okay, so that's going to be 0. And now what do I do for the next number so I know what the increments are? How do I know what 100 is going to be? Oh, I'll say a human body. The inside of a human body is going to be 100. And so he was able to get temperatures measured from people who were very conveniently just lying around because they were in the hospital. Well, they were sick. Their temperatures were a little high. And so that's why the normal human temperature is around 98.6. Different individuals, by the way, have normal temperatures that go around that. Some are lower, some are higher. But the ones he selected were 100. So that's where Fahrenheit came from. As cold as you can get on 0, weather-wise, and a human body, and then just divide it from there. Later on, this guy named Celsius says, that's kind of random. I'm going to base it on one thing, water. Okay, because water's everywhere, so I'm going to get some pure water. The temperature it freezes at is going to be 0. The temperature it boils at is going to be 100. And then it'll be really nice to use that way. So they had both of those going on, and they were in competition. The nice thing about Fahrenheit is you can be a little bit more precise without using decimals than you can be with Celsius. And the nice thing about Celsius is, 30s are hot, 20s are nice, teens are a little chilly, and, the zeros, if you will, are cold. But then you can get negative numbers, okay? The rest of the world eventually went with Celsius for talking about weather. America stayed with Fahrenheit because we like to do that sort of thing. Because we can. We've got nukes. All right, so now what about absolute zero? What they noticed was that as you shrink, as you get things colder, you get it okay? I hope it works for you. Is it charged? Okay, good. Of course, ClassLink is having a problem right now. So what they noticed as they cooled things down, the volumes of different gases and that converged towards a particular temperature that it seemed like nothing would be able to go below. They all kind of aimed at that temperature because not everything does actually obey this law exactly right. And so this guy in the 1800s, Kelvin, later on, said, I think that's about negative 273 Celsius. So that's going to be the absolute zero on my new scale. I'm going to use the same increments that Celsius did because we're all used to that size of a degree. But I'm going to put zero down at this truly absolutely coldest thing. So he kind of mixed it up. He took the size of a degree from Celsius and the idea of as cold as it gets from Fahrenheit. Does that answer your question? Kind of. Okay. So yes. What are you looking for? You're here a little early.
Isaac.
Oh, I'm sorry. I didn't recognize you. Sorry. Well, welcome back. My apologies. Just for today, do you mind sitting behind Mason over there? Yeah, thanks. That will have the 3 full rows thing. I'm so sorry. That's fine. My mistake. Do you have a pass or anything? Or? Okay, all right. Well, it's your first time back, so I'm not going to count it against you. All right. All right. So, back to this. Mole-volume relationship. Again, temperature is just conventional. Pressure is also conventional, and that's why there's like 10 different normal ways to measure pressure. But we just decided for this equation, for this R, and you can use any pressure and any volume, and it'll just change what R is. The equation stays the same. It just changes what R is. So you can look up different R's for different things here. There's even an absolute scale that uses the increments of Fahrenheit. And so it's like negative 450 degrees is absolute zero. It's called Rankine. But nobody uses that. Moles are pretty much standard, so don't use that. Okay. All right. Now, the next big idea, density. A lot of people have trouble with the idea of density, but what it is, it's a ratio. Just like molar mass is a ratio, and even the volume of a mole is a ratio. It's always 22.4 liters per mole, as it's written over there on the board, circled. That's a ratio. Anytime you have a per, a division line, that is a ratio. It's just that the denominator is 1 to make math easy. Density. So if I have a gas-filled air balloon, it will either sink or float depending on whether the density is greater or less than the density of the surrounding air. So I've gone over that already. And so moles per liter may be the same at the same temperature and pressure. But as you know from molar mass, moles and grams are not the same. And so density is going to deal with mass, big grams, not the number of particles, but just how much they weigh when you put them on a scale. Basically, it gets down to how many protons and neutrons are there in the nucleus, because the electrons don't count. They don't count. So, grams per liter. Now, all right. Again, the molar volume at STP is always going to be this, okay? 1 mole for every 22.4 liters. But it's going to be different numbers of grams per liter, okay? Now, if you take 1 over 22.4, then you're going to get like, I don't know, 0.04 or something, some not nice number. But it's a very small number of moles per liter. But the grams per liter can be a lot larger because the number of grams per mole is bigger. So, all right, how do you actually do this? How do you actually know how much it's going to be at STP? So, let's say we have a mixture at STP of carbon and oxygen, okay? And now again, this is the compound containing carbon and oxygen, not just those pure elements. If it was the pure elements, the carbon would just be sitting there in the black pile at the bottom of the thing. So it's got carbon and oxygen. So what's the molar mass of the compound? And is it going to be carbon monoxide or carbon dioxide? It's going to make a big difference if you open up the bottle. So how do we do this? Well, we get the knowns again. Get the knowns, and I didn't bring over the eraser. The eraser. Be right back. Step one, take the time to rewrite down what you know. Using your hand, and not your fingertips on a keyboard, but using your hand can actually help the brain think through things. Right? It activates different parts of the brain so you can think through things. So what do I know? Step one, what do I know? I know that the given density in this problem is 964 grams per liter. I can weigh that. I can weigh that because I can see, oh, the jar says it's a liter. I can weigh it. I know the weight of the jar itself, so I can subtract that. Everything left over is 1.964 grams. I can do that, okay? Or if it's 2 liters, then it's almost 4 grams, whatever. I can do this directly. And then, so that is a fact, okay? So again, given the density here is that number, it's going to change from problem to problem. But a rule, something that doesn't change from problem to problem, is that the molar volume is going to be 22.4 liters per mole. Okay? I've got 22.4 liters per mole. That is just always going to be true. Now, what do I not know? Okay, what is unknown is going to be the molar mass. All right, so what's the molar mass? And we can use like a couple of capital M's for that. Molar mass is going to be what? Grams per mole. The key thing here is look at your dimensions. Look at your dimensions. Look at your units, okay? If I want grams per mole, and I've been given a couple things that have liters, one has grams and one has moles, aha, I am going to multiply those and get rid of, cancel out the liters. So, step 2 is going to set up. And I'm going to take the density times the molar volume, and that will give me the molar mass. Okay, so the density times the volume sub mole and the mass per mole. Okay, so, or not per mole, but just the molar mass. So I should get grams per mole. And if I put in the numbers, then it'll be such and so many grams per liter times such and so many liters per mole. Grams per liter times liters per mole. Grams per liter times liters per mole. The liters will drop out, and I will get grams per mole. You see how that works? Now I just have to plug in the numbers. So it's 1.6964 grams per liter and 22.4, I don't know why I keep looking up that, liters per mole. The nice thing is both denominators are 1. Yay! I love multiplying by 1 on the denominators. Makes it so easy. So I just plug those two numerators into the calculator, and I get 44.0 grams per mole. 44 grams per mole. 44.0 grams per mole. Yes?
So, signature 15?
Significant figures, yes. Yes.
So, you put this was 1.92494?
It does have 4.
So is the 44.0?
It's limited by the 22.4.
Okay.
Now you can look on Google and find a more exact volume for the mole, the molar volume. You can, but all that you need to know for this class or even in college is 22.4. That's enough. 3 sig figs is pretty good. So even 2 is acceptable. 1 is why did you even bother? But so 2 or 3 is kind of the sweet spot. 4 is maybe getting a bit excessively accurate, or precise, I should say. So 44.0, and now the next question I have is, does this make sense? Is there any such compound with carbon and oxygen that has this? And I know we're almost out of time, but can I think of CO or CO2 or any other carbon and oxygen compound? Could this be a real thing? Well, if I have carbon and oxygen, just carbon monoxide, it's 16 and 12. That is what? What's the sum of 16 and 12? You do not need a calculator for this, people. 28, very good. Well, 28 isn't 44. What if I had another oxygen, another 16? 28 and 16? 44, so it is possible. I've got carbon dioxide. Yay! Okay, so you are about done, and I'm going to go ahead and stop the video.